Hello, everyone. Thank you for your attention this afternoon. My name is Douglas Blumeyer, and I'm glad to have this chance today to speak with you about Sagittal, the Universal Microtonal Notation System. This is going to be a sort of crash course tutorial. I will assume some entry-level understanding of microtonal concepts, but I'll try to provide refreshers on things as they go along. I hope you will come away from this presentation feeling inspired to compose some microtonal music using one of Sagittal's notations, and, of course, knowing how to do it. I did not create Sagittal notation. Credit for that goes to Dave Keenan and George Secor. It was created by them in the early 2000s, along with input from members of various online microtonal communities on the Yahoo Groups website. The extent of my involvement with Sagittal is that I've been volunteering a large amount of my time in recent months to help update its online resources. I've also started building some new online tools, but I don't have anything ready to share quite yet. Stay tuned by joining the Sagittal online forum. I've broken this presentation down into 3 sections, working up through increasingly advanced Sagittal notation concepts. There certainly are some things I'd define as advanced topics, but I'm stopping at intermediate level concepts today because that's all we'll have time for. So, let's begin. In this introductory section, we'll simply cover what does Sagittal notation look like and why. Your first question might be, why the name Sagittal? It comes from the name of the Greek mythological figure Sagittarius, the archer, pictured here. The Sagittal notation system has a sort of ancient Greece theme to it, beginning with its name. And the reason for the association with archery is because each Sagittal symbol looks like an arrow. Speaking of which, it's certainly time by now to take a closer look at some of those arrow-looking Sagittal symbols. Here are a few of the most common Sagittals. Now that's right, for short, we can call Sagittal symbols simply Sagittals, with a lowercase s. Each Sagittal is a member of a pair, one up and one down, but by the same amount. As you can see here, up and down pairs are not 180-degree rotations of each other, they are vertical mirrors of each other. Let's look at the elements that Sagittals are built out of. The vertical line that every Sagittal symbol shares is called the shaft, like the shaft of an arrow. And the parts that hang off the sides are called flags. Shafts are all the same, but there are different types of flags. The straight flags are called barbs. The curved out lines are called arcs. And there are 2 more flag shapes, but we'll meet them later. We can use the flags to name the symbols. For example, we could call the leftmost symbol the left barb, and we could call the middle symbol the right arc. The symbol on the right has both a left barb and a right barb, and so we can call it the double barb symbol. From now on in this presentation, I'll be using orange, green, and blue to help highlight patterns in the diagrams I show when these 3 symbols, or their commas, are involved. Speaking of commas, every Sagittal has a primary comma. It's a comma, or a small, justly intoned interval, and it's primary because it's not the only comma the Sagittal can represent, but it is the main one. Each Sagittal has the potential to represent any value from within a range of values, but in the absence of other specification, this is the one you should interpret it as. In other words, a Sagittal's primary comma is its default value. Unlike many other microtonal notations, every Sagittal's value is flexible. You can't be a universal microtonal notation system, allowing people to translate meaning between various tunings without your symbols having flexible values. More on that in a moment. Here are the sense values of those commas. This shows how they are sorted in order, left to right, in increasing size. And this shows a helpful design principle which Sagittal adheres to. It's that the size of the area occupied by the symbols roughly corresponds to the size of the pitch alteration the symbol represents. In other words, the shaded areas get bigger from left to right at about the same rate as the pitch. The big benefit here is that when sight-reading Sagittal notation, even if you momentarily forget a symbol, its visual size should give you a pretty good idea how much to adjust pitch by. So okay, you're probably still curious, when would a Sagittal ever indicate a pitch alteration other than its default value, its primary comma? Or in other words, what kinds of other specifications might we expect to come across to deviate a Sagittal from the value shown here? Well, how about an EDO, that is, an equal division of the octave? Yes, these three symbols also happen to be the ones which Sagittal uses to notate 72 EDO, one of the very most popular and important EDOs. They notate the first three steps of 72 in that order. Each of these steps of 72 is quite close in value to the primary commas of these sagittals. So while it is certainly possible to simply memorize the sagittals for your favorite EDO, if you go a little further and familiarize yourself with their primary commas, then you may find that they lend some helpful insight into the harmonic functions of the pitches in your tuning. Here's an ascending chromatic scale on C in 72 EDO, notated in sagittal. You can see that we only need these three sagittals, in combination with the conventional sharp or flat symbols, to notate every pitch. Essentially, the sharp symbol here is 6 degrees of 72, and the 1, 2, and 3-step alterations sagittal provides lets you fill in all the blanks. This chart is pretty repetitive, so let's zoom in on just one measure to get a closer look. The first 3 steps are easy. Use the 3 sagittals provided. And then, once you get to the 4th step up, you can think of it as 6 degrees up, 2 degrees back down, and notate it by combining a conventional sharp with a sagittal for 2 steps, but its downward mirror. And for 5 steps up, you achieve 5 as 6 minus 1 by combining a conventional sharp with a downward sagittal, but this time the one for only 1 step. Look at the pattern in the colors. They proceed through orange, green, and blue, and then go backwards again from blue to green to orange. If we really wanted to, we could have written the 3rd step up as a sharp up and the 3-step sagittal down. In other words, plus 3 equals 3, but so does plus 6 minus 3. But why would we use 2 symbols when you can get away with using only 1? Generally, we should opt for the simpler notation whenever possible. Now, some of you with some previous familiarity with sagittal may already know that there is a way to use sagittal notation whereby conventional sharps and flats are no longer needed at all. If so, don't worry about that yet. I'm showing it this way first because it's easier to understand. We'll talk about the other style a bit later. Now let's look at some extended JI. Of course, in the microtonal community, it's a good idea to play fair between EDO and JI. So, here we have an 11-limit tonality diamond on D, notated using these same 3 sagittals. Thanks goes to Cam Taylor for the original diagram, which I modified for this purpose. He went up to 45 odd limit in his original. Some of you no doubt recognize these ratios. 80 to 81 is the syntonic comma, 63 to 64 is the septimal comma, and 32 to 33 is the undecimal comma. These are the most important commas in the 5, 7, and 11 limits, respectively. You can see here that, unlike with the EDO notation we just looked at, sometimes multiple sagittals are used on a single note in order to reach the desired pitch. And sometimes we even have to use some sagittals pointing up while some are pointing down, such as with notating the ratio 10/7 here. This is certainly not ideal yet. Let's take a closer look. Here's a select few sagittals combining with each other in a similar way. So I should say now that while what we're looking at here is completely valid sagittal notation, it is not the preferred sagittal notation style. I'm showing it to you here first, again, because it's the absolute simplest notation to understand. Move by a 5-limit comma, add a 5-limit comma to sagittal. Move by a 7-limit comma, add a 7-limit comma sagittal, and so on. So it's simple to understand, sure, but the result is a bit cluttered. This style is very similar in principle to many other microtonal notations, and so sagittal offers it too. But in the next section, we'll look at how sagittal additionally offers a different approach in an attempt to improve on this situation. Great, so that concludes the gentle introduction to sagittal. Now it's time to look at some sagittal basics. In this section, we will identify 3 different sagittal notations: EDO, prime factor, and JI. By the end of this section, we will completely understand how to use the first 2. As for the JI notations, we'll delve deeper into those in the following section. So let's first look at EDO notations. Here's a set of some of the most popular microtonal EDOs, shown with the sagittals you need to notate them. You can see at the end of this list is 72 EDO, with the 3 symbols we used to notate it in the introductory section. All but 53 EDO shown here can be notated using only those 3 symbols. We'll meet that other symbol in 53's box in just a little bit. You may wonder, but how can the same sagittal notate one step of 17 EDO, but be the same symbol used to notate one step of 31 EDO, which is nearly half as big? The answer to that is, the appropriateness of a sagittal has less to do with its size and sense as it does with its likely harmonic function, given the mappings of its primes in the given EDO. More on that later. You may also wonder, how would I know, for a given EDO, which sagittals to use? Or in other words, where in the world did I get these pretty colored boxes here? Well, that's a very pressing question, and one that we'll answer right away. For that purpose, a table was developed by the sagittal co-creators, which shows the sagittals for every EDO up to 72. And here it is. It's affectionately referred to as the periodic table of EDOs. Clearly, there's a ton of information here. The positions of the EDOs in this table can tell you helpful things about how they relate to each other. But we don't need to drill down into that right now. This is the beginning of the basics section, for crying out loud. But if you're just waiting for me to show you where the sagittal EDO notations live, so you could run off and get to work, well, now you can. This chart is the first thing you'll see when you visit Sagittal's homepage, so you're ready to go. But I think it would be really helpful if we spent a little more time explaining how to derive your notation from this chart. The basic idea is each of these boxes is a different EDO. The symbols shown are shorthand, giving you just the symbols you need, in combination with a sharp and flat symbol, like we showed for 72 EDO in the introduction. One of the things I'm working on for Sagittal now is a full example of each EDO notated on the staff, like I showed for 72 earlier, that maybe you could get to by clicking on each one of these. So that's nice to have, but in the meantime, what you need is fully derivable from this diagram. So let's work out some examples, though, shall we? Well, what better place to start than 12 EDO? Not exactly microtonal, but it will help to ground us. So, wait a moment, the box is empty, besides the number 12. What are we supposed to do with that? Well, remember we said that the box gives you a sagittal for every step until you reach the sharp, but that doesn't include the sharp. And so in this case, the box is telling us that there are no sagittals needed between the natural and the sharp. In other words, 12 EDO can be notated entirely with sharps and or flats. The same happens to be true of 19 EDO. It's just that in 19 EDO, C sharp is no longer the same note as D flat. Okay, but this isn't sagittal notation, you might say. Well, remember, there's more than one way of using sagittal, and one way of using it still keeps the conventional sharps and flats around. So this is technically valid sagittal notation. There's just nothing uniquely sagittal about it. If you're curious, here's what 19 looks like in the sagittal style, which rejects conventional sharps and flats. We haven't seen this symbol yet, and you don't need to worry about it yet, but that's basically sagittal's own sharp and flat symbol. Sharp when pointing up, flat when pointing down. I think it's kind of nice how this makes the relationship between sharp and flat more clear. Like any other sagittal, they're the same alteration, just in opposite directions. Okay, let's try another example. Another popular EDO, 31. This time we can see that we get one set symbol to work with, the double barb. So we can probably feel pretty confident about starting out like this. But what next? Is it a C sharp, or have we already reached D? For 12 EDO, we could answer that question without thinking about it. We're so familiar with the diatonic shape 2-2-1, 2-2-2-1 that we can hardly forget about it. What's the shape in 31 EDO? To answer that question, we need to know the fifth size. Basically, it's whichever step of 31 EDO gets you closest to the fifth, aka the frequency ratio 2-3, or about 702 cents. This part isn't too hard to figure out how to work out on your own, so I'll just tell you the answer. It's 18 steps. So, how then do we get the rest of the steps? Well, we get them the same way we get the 2-2-1, 2-2-2-1 in 12 EDO. we follow the circle of fifths. If we're starting on C, and we want to fill out the rest of the bare nominals, we've got 1 down to go to get to F, and then 5 up, G, D, A, E, B, to finish the rest. In 12 EDO, the fifth is 7 steps wide, but in 31 EDO, we know it's 18 steps. So each time we move by 18, so it goes 18, 36, 54, etc. Except each time we pass 31, we have to loop back around, so it's not actually 36, it's 5. So in the end, that gets us a similar diatonic step pattern of long, long, short, long, 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 short, but this time it's 5, 5, 3, 5, 5, 5, 3. So we're certainly not at D yet, if we've only gone 1 step, but what about C sharp? How many steps does it take to get there? The quick, kind of cheating answer is 2, because the box only gives us 1 symbol, so we already know the next symbol is the sharp. But we can confirm this answer by continuing our circle of fifths iteration process. If we go 1 step further up from B, we reach F sharp, and by comparing its position to F, 2 steps away, we can now confirm that in 31 EDO, the size of a sharp is 2 steps. So let's apply this knowledge to the interval between C and D. If it takes 5 steps to get from C to D, then there are 4 steps between C and D. From C upwards, 2 of those steps will be our sagittal and the sharp. And from D downwards, we can use the mirror image, our sagittal downward and the sharps downwards, aka a flat. So there we have it, C to D. Or in other words, we've now notated one of the 5 whole tone intervals in this EDO. This is the same thing as one of the 5 longs in that long, long, short, long, 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 short diatonic pattern. Each of the others will be a copy and paste of this, transposed of course. So the only real problem left is how to notate the lemmas. That's the fancy word for the 2 short intervals in the diatonic pattern. Well, we can use the same process to notate those. Let's take E to F as our example. If there are 3 steps to a lemma, then that means there are 2 notes in between E and F, and we'll divide that in half, because it'll be a mirror, with half those notes based on E and half of them based on F. So that's simply 1 note for E and 1 for F. Well, we have 1 sagittal to work with, so E gets that sagittal up, and F gets that sagittal down. It's not too hard after all. So now we can just copy and paste these patterns around, and voila, we have 31 EDO. So that's the last example I'll give for now. I'll give you a few moments to absorb it. But I also can't help but share the version using sagittal's own sharp symbol. So not only do we see the benefit here where it's clear how sharp and flat are the same alteration, just in opposite directions, it's also obvious how a sharp is 2 steps and the other symbol is just 1 step. They have the same flags, just a different kind of shafts. So it's more internally consistent and obvious once you get used to it, of course. Alright, that's enough tutorial on deriving EDOs from the periodic table for now. Full disclosure, that process will not work for every EDO. When you try to use wacky EDOs around the fringes, the gold and rose ones, things behave a little differently, but we don't need to worry about those for now. The periodic table is pretty well set in stone, but the sagittal community has also determined many notations for EDOs beyond 72. These can be found in various places if you need them. Every once in a while a new EDO gets brought up on the forum, discussed, and decided upon. Some EDOs have multiple options. It's a complicated business, choosing an EDO notation, and also not appropriate to discuss here now. But most mortals don't need to understand the full decision tree for creating a given EDO's notation. In general, you should just trust the community did its job and that you have the best sagittals for the purpose at hand. Okay, let's look at the next sagittal notation, the prime factor notation. First, we're going to need to meet some more sagittal symbols. So the 3 sagittals we looked at in the introduction are all members of the first subset of sagittal symbols. It's called the Spartan symbol subset. What you're looking at is the full Spartan set, 8 symbols. Well, it's not exactly the full set. Each of these, of course, has a mirrored pair, and, well, there are some other Spartan symbols too, but we'll get to those later. For now, let's just focus on these 8. If you're previously familiar with sagittal, you may be aware that it's capable of notating a great variety of tunings, and to an extreme, or some might even say insane, precision level. And in order to do so, in total, there are over 100 sagittal symbols. But don't let that number scare you. Almost no one will ever need to know or use most of those symbols. The 8 Spartan symbols shown here may be the only ones you ever need to learn. They are enough to notate a good chunk of microtonal music. I should point out that the first symbol here uses a flag shape we haven't mentioned yet. It's called a scroll. It's curved, like the arc we see on several of the other symbols here. Let's make a more direct comparison, though. So we can see that the scroll is much smaller than the arc, corresponding, as you know, to the size of pitch alteration it represents. Also, its shape is different. It's concave, that is, curved in toward the shaft. The arc, on the other hand, is convex, curved away from the shaft. These symbols are in order, from left to right, in the size of the pitch alteration they represent. Here are their sense values to clearly demonstrate that. And you can see the size proportionality principle continues to hold here. So why the name Spartan? Well, here's that ancient Greece theme showing up again. The ancient Greek city-state of Sparta was famous for its lifestyle unburdened by excess, so much so that the word Spartan entered the English language meaning rigorously simple, frugal, or austere. And that vibe suits this symbol subset well, since it is the smallest symbol subset in sagittal, and yet it can do so much. It's extremely economical. Here are the Spartan symbol's primary commas. Again, you can see the syntonic, septimal, and undecimal commas, highlighted in orange, green, and blue, respectively. But most of these others ratios may seem a bit obscure at first. They use way bigger numbers. You may wonder why they're so different from the first ones we looked at. Well, the truth is, they're not really all that different in the ways that actually matter. Most of the bulk of those ratios is not particularly relevant. In order to more clearly see what is important, it's instructive to remove all the factors of 2 and 3 from them. And here's what that looks like. Suddenly, it's crystal clear how the syntonic comma is aka the 5 comma, the septimal comma aka the 7 comma, and the undecimal comma aka the 11 comma. Those numbers are the single prime factors beyond 2 and 3, which these symbols introduce to their pitch. And we can see how all the other pitches that used to look so imposing are really no more than combinations of 1 or 2 of these same 11 limit primes. These 2-3 free classes are what we use to name sagittal commas, so we don't have to use the full ratios. So, why remove all the factors of 2 and 3? Or maybe, how can we get away with that? Well, that question gets at the very foundation of JI notation. And while it's a bit involved, this one we do kind of have to tackle now, or else nothing else that follows may make enough sense. The simplest answer to the question, why remove the factors of 2 and 3, might be because you don't need to use them in JI notation symbols. That part is already a solved problem, built into the foundations of the conventional notation. 2s and 3s are handled by the 7-note letter names, F, C, G, D, A, E, B, and octaves thereof, spaced vertically on a staff with horizontal lines, along with sharp and flat signs, and double sharp and double flat if need be. Microtonal symbols are only needed for deviations from this foundation. Let me get a bit more specific, though. Each 2 in a pitches ratio can be handled by shifting a note to the next one with the same name. For example, C4 to C5, or A4 to A3. We can see that here with each vertically aligned pair of notes. And each 3 in a pitches ratio can be handled by changing the letter to the next letter in the sequence, for example, C to G, or A to E. And once you go off the edge, you must tack on a sharp or flat and wrap back around, for example, B to F sharp. Many people are familiar with the circle of fifths, seen here on the left, but this only pictures the situation in 12 EDO, standard tuning, where moving by 12 fifths takes you right back to where you started. And if you remember our work with 31 EDO earlier, when we moved by steps of 18, well, we would have eventually gotten back home there too. EDOs are closed systems. They circle back home. Far less commonly spoken about, but more important to JI notation, is the spiral of fifths, seen here on the right. Images on this page were adapted from Lucy Tuning at harmonics.com, by the way. When you use pure Pythagorean fifths, that is, the exact frequency ratio, 2 to 3, a C sharp does not come out to be the same thing as a D flat. We say they're not enharmonic. So you could keep spiraling out forever and get further and further away. That's why it's a spiral and not a circle. We have to cut ourselves off at some point, and so I've stopped here after exhausting all of the double flats and double sharps. So if we return to this view, I should note that although we've got 70 notes on the page here, in 12 EDO, we've still only got a total of 12 pitch classes. A lot of these overlap with each other. So knowing this circle of fifths in 12 EDO can help you understand certain things like how keys are related to each other, but it's not strictly necessary to understand. You could go your whole life simply thinking a sharp simply means move up one step, and a flat means move down one step. But in just intonation, there are 35 different pitch classes here, one for each vertical slice. They're all different, and each sharp and flat means moving 7 times by the 2 to 3 ratio, then 4 times backwards by the 1 to 2 ratio to arrive close to where you started. To account for the 4 times your spiral made its way around the circle. And why is all this important then? Well, it means that when notating JI music with this foundation, we already have 35 anchor points from which we can apply microtonal accidentals. If those accidentals happen to have a bunch of 2s and 3s in their primary commas, like we saw some of the Spartan symbols do, that's okay. It just means we have to find the ideal anchor point out of those 35. And by ideal, I mean the one which has a number of 2s and 3s that will cancel out with many of the commas 2s and 3s. That way, the end result is a recognizably small and popular JI pitch. Look at it this way. Here we've got our 35 anchor points along the Pythagorean chain of fifths, rooted on D. Well, actually to save space, I didn't even go to the double sharps or flats, so it's only 21 of them, but same difference for these purposes. So you can see how a sort of hourglass shape is formed, where close to D, the ratios are very small, and as you get further away in either direction, they get bigger. Now I've added a column to the table to show you what pitches you get when you apply a left barb down sagittal to that note. On D itself, we can see that we notate the syntonic comma itself, the ratio 80/81. Interesting, sure, but we don't often actually use that pitch in a scale. It's so close to the 1/1 root. The pitches we're usually interested in are a little ways up. 10/9, 5/3, or 5/4. In other words, the smaller, simpler ones. You can see here that this section has its own hourglass shape, but it's offset from the base Pythagorean chains. That's because the syntonic comma down, in addition to its all-important prime factor of 5, has 4 2s in its numerator and 4 3s in its denominator. That means that those 2s and 3s are going to cancel out wherever the Pythagorean fifth chain's anchor point has 3s in its numerator and 2s in its denominator. In other words, the syntonic comma down is going to be handier in a section of the Pythagorean chain where we've already moved up by about 4/5. Much farther from that, there are just going to be too many leftover 2s and 3s in the ratio for it to be harmonically interesting. Conversely, we can look at the syntonic comma up and see that it also exhibits this hourglass shape with small numbers in the middle and big numbers at the edges, but its hourglass is offset in the opposite direction. So the most interesting pitches it notates, 6/5, 8/5, 16/15, are found after moving down by about 4/5. So when a microtonal accidental has a large number of 2s or 3s in its comma, this doesn't mean that it's unusable. It only means that it's more usable in a vicinity of the chain of Pythagorean fifths, which is further away from your 1/1 root pitch. The pitches that have very few 2s or 3s in their commas, conversely, are more useful nearer your 1/1 root pitch, and less useful further away. So it can actually be helpful to have multiple symbols with the same 2-3 free ratio, but different amounts of 2s and 3s, to most fully cover your bases throughout the usable part of the Pythagorean chain. At a certain point, if a comma has so many 2s or 3s in its ratio that you'd have to go beyond double sharps or double flats to use it, then, yeah, it ceases to be useful. but all the commas used by Sagittal are well within that range of usefulness. Alright, so now that we've covered the foundations of JI notation, at least for octave repeating JI, we should move on. Not even going to touch non-octave tunings today. Alright, so earlier on, I said that this style of sagittal notation, with more than one sagittal allowed per note, was not the preferred style. And that is true, but I also said it was a valid style, and that's still true too. And the style has a name. That name is prime factor notation. So named because each symbol represents a single prime factor of the pitch being notated. I also said earlier that using sagittal in this style was similar to other JI notation systems. So let's do a compare-contrast with extended Helmholtz-Ellis JI prime notation. Even as an acronym, EHEJIPN is long to say, and I think they like to use just HEJI for short, so let's just call it HEJI. So Sagittal's prime factor notation is almost a substitution code for HEJI. One difference is, Sagittal and HEJI made some different decisions about which exact commas to choose for each prime factor. It's viable to choose a comma with the same prime factors above 2 and 3, but completely different counts of 2s and 3s. Sagittal and HEJI diverge on their choices for 17, and then it looks like they diverge for every prime past 43. So that doesn't actually affect us here down in the 11 limit, just FYI. And they clearly make different stipulations about the order of the symbols. I admit that I don't know exactly what the rule is for HEJI. And to be fair to HEJI, it is not the case for them that every one of their prime symbols stands alone, as is the case in Sagittal's prime factor notation. They make an exception for factors of 5, which instead of needing their own symbols, simply tack on to the conventional naturals, sharps, and flats as little arrows pointing up or down, as you can see here. And they also have a special case for 2 7 commas, which lets them collapse together, which you can also see here. But let's get back to Sagittal, though. Here's a diagram showing the first 4 symbols in the prime factor notation, or in other words, the first 4 prime numbers beyond 2 and 3, which are 5, 7, 11, and 13. What's notated here is the harmonic series from the 4th harmonic to the 13th. We can see here how, of these first 4 primes, 3 of them involve a downward shift of pitch in order to hit the pure harmonic. These are the 5, 7, and 13. Only the symbol for the 11 applies an upwards adjustment in pitch. Now, if you want to go past the 13 limit, you begin to require non-Spartan symbols, so we'll stop here for now. The remaining symbols, if you need them, can be found on Sagittal's website. So far, they've been specified up to the 61st harmonic. If for some reason you need to go beyond that, there's a documented process for determining the correct symbol. If you do happen to work further symbols out, it'd be great for you to share them on the Sagittal forum for the benefit of the rest of the community, but probably you don't need primes past 61, unless it's for some theoretical purpose. Humans can't really hear harmony with that level of precision anyway. For most humans, the 13 limit is just fine. And with these 4 symbols, it is possible to exactly notate any pitch within the 13 limit. The only limit is how many symbols you're willing to load onto each note. Alright, so it's time for part 1 about JI notations. So yes, the prime factor notation we just looked at is for notating JI, but Sagittal has another more important family of notations which it calls its JI notations. So I pulled up again those same select few pitches which have been notated using more than one Sagittal apiece. And there's even one of them with Sagittals pointing in different directions. These are 2 things the Sagittal co-creators wanted to make possible to avoid. And it is indeed possible to avoid both of them in Sagittal. Avoiding them is a key difference between the simpler prime factor notation, which you already understand, and the JI notations, which we're just getting started learning. Here's what it looks like if you use just one Sagittal per note. Much better. So, since this is Sagittal's preferred JI notation style, this is what Sagittal calls simply its JI notation. Of these 3 symbols, you may only recognize one of them from the Spartan set, the one on the left. Don't worry, we'll look at the others later. But now is a good time to illustrate how to convert between these 2 equivalent notations. How do we get from the multi-Sagittal notation to the one Sagittal notation? Let's first look at how to derive that first symbol, the one that we do find in Spartan. what we have here is a very basic example of what we call element arithmetic. Remember, flags and shafts are both symbol elements. When you merge a single flag symbol with another single flag symbol to create a new symbol with both flags, it's often as simple as exactly combining the values of the original two symbols, that is, their primary commas. In this case, it is indeed exact. If you multiply 81 over 80 by 64 over 63, you get 36 over 35. By the way, whenever element arithmetic is not exact, it comes out very close, by within 2 cents. Alright, now let's look at the next example. This one is a little trickier. Remember how opposite sagittals are mirror images of each other? Well, look at the first two flags in this diagram. They're on two different symbols, and one is up and one is down, but they are both left barbs. They are mirror images of each other. So, they represent the same pitch value, but in opposite directions. That means these two flags cancel out. What remains is only the flag on the right side. Let's look at what's happening here in another way, with the 2's and 3's removed again, so basically looking at the comma names. We could say that the right barb is defined as the 55 comma, that is, a 5 comma combined with an 11 comma. If you're wondering why that's a positive 5, even though the sagittal for the 5 comma is pointing down, that's because, as we saw a little earlier, the downward 5 comma sagittal represents 80 over 81, for which the 5 is in the numerator. So, when you're using it to increase the number of 5s in the numerator of the ratio, you're actually moving downwards in pitch. Perhaps this is easier to grasp if we refactor this equation a bit, so it looks more like the simpler one we encountered first, where visually, all you'd have to do is squish the two symbols on the left together, and you'd get the one on the right. So you might read this picture as the 1 over 5 comma combined with the 55 comma gives you the 11 comma. So the left barb up symbol may be called the 1 over 5 comma because its 5 is in the denominator. And you might notice that in this case, it doesn't look exactly like if you squish the two symbols on the left together, you'd get the symbol on the right. You can see that the left barb is a bit smaller than the right barb. That's because it represents a slightly smaller pitch alteration. It's important here to note that while left barbs and right barbs share a flag-shaped name, they represent different values. In other words, a left barb would never cancel out with a right barb. You wouldn't even compare them. The same goes for the other flag shapes like arcs and scrolls too. Left arcs and right arcs just represent completely different values. Stepping back out again, we can now see how every symbol we've seen so far with multiple flags can be derived from the two single flag symbols, which each have one of its flags. We only need to meet one more symbol, the left arc, which represents the 7 over 11 comma, to see how this family of symbols is all interconnected. I'd like to note in particular how, when you combine two left barb symbols, you get a double left barb symbol. The barbs just space apart vertically and change angle a bit for readability purposes. Now, to be clear, you don't have to do this sort of elemental arithmetic yourself in order to use sagittal notation. You shouldn't go trying to invent new sagittal symbols yourself by combining flags together that haven't been combined before. All the valid sagittal symbols you should use have already been created, and this information is built into them as they are. This is really only just some extra information that's there for you, in case it's ever helpful for you to unpack it. Using only these 8 Spartan symbols for extended JI, using only one of them per note, it would be possible to exactly notate an extensive 5-limit pitch matrix, up to 4 5s in the numerator or denominator, all of the 9-limit constances exactly, and the 16 harmonics and subharmonics, with the sole exception of the 13th harmonic, which is approximated closely. In order to understand how you would use these symbols to approximate the 13th harmonic, however, you'll need to learn more about the sagittal JI notation. As forewarned, as we come to the end of this section, you still don't have quite enough information to completely use the sagittal JI notation. Don't worry too much. We'll complete your training very soon. And here we are. So, are you ready for some intermediate level sagittal concepts now? In this section, we'll be covering the following topics: multi-shaft symbols and the 2 flavors of sagittal, capture zones and precision levels, which are the topics we still need to cover in order to get you off and going with sagittal's JI notations, and a new notation, the 12 relative notation. So without further ado, multi-shaft symbols and the two flavors of sagittal. The first big question we're going to answer here is, how can sagittal be used in a way without conventional sharps and flats? The answer is multi-shaft symbols. With this answer, we simultaneously answer a different question that was posed earlier, but had its answer deferred. That question being, what are the other Spartan symbols? Yes, these 5 new symbols are in the Spartan sets, too. I didn't show them to you earlier because at that time I was just trying to show you the minimum amount of information to start basically using sagittal. To be more specific, you might never need multi-shaft symbols because you only need multi-shaft symbols if you want to use sagittal without conventional sharps and flats. And thus, the multi-shaft symbols are synonymous with what we call the revo flavor of sagittal. The flavor we've been using up until now was called evo flavor. The revo flavor adds another layer of complexity to learn up front, but then, after investing the time to learn it, what you read and write on the page can be simpler and cleaner than it could be with evo. The flavor is called evo, short for evolutionary, because it preserves the conventional notation and evolves it to include sagittals. And this new flavor, revo, is short for revolutionary, because it completely overthrows the conventional notation, replacing it with a new sagittal order. To be absolutely clear, when I say that the multi-shaft symbols are synonymous with revo, one thing I mean by that is, if you see conventional sharps or flats on the page, then you should never see multi-shaft sagittals. Mixing evo and revo flavors is a no-no, like mixing chocolate and garlic or something. Both great flavors, but not good together. We used to call these two flavors mixed and pure, but after much discussion decided that the names evo and revo should do a better job of conveying the difference between the two flavors. If you've been using sagittal for a while now, though, you may have come across them as mixed and pure. And it's still that way in some materials out there on the sagittal site. Again, one of the things I'm working to update. So, to be perfectly clear, these are just two pairs of names for the same thing. One old pair of names, one new pair of names. Unlike the situation between the JI notation and the prime factor notation, where the JI notation is definitely preferred and the prime factor notation is not recommended, neither of these two flavors of sagittal are preferred by the community. They're both equally accepted. In fact, one of the sagittal co-creators preferred one, and the other co-creator preferred the other. I won't tell you which liked which, though. Now, there's a lot going on here, but let's take some time to look through it all. Both of these rows are sorted in increasing size from left to right, from natural to sharp. You probably recognize the order of the 8 single-shaft Spartan sagittals, which we already learned. Each pair of vertically aligned accidentals is equivalent. Most of them, in fact, are identical, until we reach the last section where evo uses the conventional sharp symbol and revo uses the multi-shaft symbols. Let's focus at the evo row first. We haven't seen this exactly before, but it should remind you of what we saw with the 72 EDO notation in the introduction. That is, at the point we introduce the conventional sharp symbol, we need to also start including a downward-facing sagittal to counteract some of the sharp's pitch alteration. You may be wondering, why doesn't the conventional sharp enter the picture precisely at the halfway point? Why does it wait a couple steps past halfway? Well, that's due to something called the 60% rule. Even though sagittal could stop exactly halfway up, or at 50%, it's a good design principle to give people the option to use a single symbol, or a single shafted symbol, as it were, to reach a bit beyond the halfway point by an extra 10%, because that's just such a common need to go that far. Alright, so then to continue moving upwards in pitch, we reduce the size of the downward-facing sagittal until it is nothing. So we're actually counting backwards. You can see that it corresponds to the 5th symbol from the start, the double left barb up. Then it's the right arc, the left barb, the right scroll, and finally natural. So what this is telling us is that the multi-shaft symbols of the revo flavor are like a substitution code for the combinations of conventional symbols and single shaft symbols in the evo flavor. Let's get a closer look at just these then. You may ask now, is there a pattern between the flags of evo and the flags of revo? Because looking at this, it certainly doesn't seem like there is. We see a double left barb becoming a double scroll, a right arc stays a right arc, a left barb becomes a right barb, and so on. Huh? The answer is no, not really. There's not a pattern. It's certainly possible to explain precisely why the Revo flags are what they are, but it involves some rather advanced ideas, so we're going to put it off for now. At this point, it's better to simply memorize them. In particular, if you use Revo flavor, you'll be seeing that last Revo symbol a lot. You may remember that we snuck it in a while back in the basics section when showing 19 EDO. That's Sagittal's own sharp symbol, or when it's pointing down, Sagittal's flat. It's the double shaft, double barb. We've got better names for all these symbols, by the way, where you don't have to describe every single element to name them. It's called Sagispeak. For example, in Sagispeak, this symbol is called Vi. Unfortunately, we don't have time today to cover Sagispeak, but if you're interested, you can learn about it on Sagittal's website. Here, finally, are all the Spartan symbols. Well, again, this is only the upward set. Each one of these here has a downward version, too. The new ones are in the second row. These are the triple shaft Spartans and the quadruple shaft Spartans. Except, clearly, when you have 4 shafts, we don't draw them that way. Instead, they become an X. And so we don't actually call them quadruple shaft Sagittals, but rather X-shaft Sagittals. This decision was made for readability. Once you have 3 or more shafts, it becomes far too difficult to instantly distinguish them with your eyes when sight reading. The X shape really helps with that. But what do the Sagittals in the second row represent? Well, let's review what the first row is exactly again, first, in an effort to make that clear. The first row starts with the smallest Spartan sagittal and proceeds up in size to the sagittal which is equivalent to the conventional sharp. The second row does the same, except it starts with the smallest Spartan sagittal just above the sharp and proceeds up in size to the sagittal which is equivalent to the conventional double sharp. So it's all one big continuum. I aligned them in 2 rows like this to show how the exact same pattern of flags is used for each iteration, from one sharp to the next. And what lie beyond the double sharp? Well, in sagittal at least, that's sometimes referred to as the edge of the world. Here be dragons and such. Theoretically, you could keep adding more and more shafts, inventing new ways of Xing them or something, but Sagittal doesn't describe it or recommend it. Up to a double sharp should be enough. Beyond that, and you're so far removed from the note you're modifying that you really should probably use a different note anyway. So, why would you want to use the Revo flavor then? Well, there are a couple big reasons. Remember the design principles we talked about earlier. No more than 1 sagittal per note, and no opposing sagittals altering the pitch in opposite directions. Well, by using the JI notation, rather than the prime factor notation, we accomplished that much. But we can take these principles and make them even stricter. What if we wanted to restrict ourselves to just 1 symbol per note and have no opposing symbols at all? Looking at the Evo flavor, we can see that they break both of these stricter principles. 1, they have 2 symbols per accidental, 1 sagittal and 1 conventional. And 2, the sharp alters the pitch in one direction, up, while the sagittal alters the pitch in the other direction, down. So, Revo was devised to offer an alternative to this situation. So, to recap, it's harder to learn Revo, more symbols to learn, more concepts to understand, but the end result is simpler. Less symbols on the page, less math in your head on the fly to move in one direction by a bit and then back the other direction by a lesser bit. When choosing which flavor of sagittal to use, it's really up to you which burden you most want to alleviate for yourself in the use of your music. Okay, enough about Revo flavor and multi-shaft sagittals for now. It's time for a completely different concept. Let's return to the topic of JI notations for part 2. Recently I teased how the Spartan symbol set, despite clearly being 11 limit, could approximate the 13th harmonic. But how could it do that? The answer is capture zones. Remember how earlier it was said that each sagittal has a primary comma, but is capable of representing any value from a range of values. Previously we saw how this could allow a sagittal to work for a step of an EDO, where its primary comma has been tempered or slightly distorted to fit the EDO's interval size. Well, a capture zone is a special name for such a range when it is used in the context of a JI notation. Any comma that is inside a sagittal's capture zone, which is not its primary comma, is called a secondary comma. What we see here is a series of capture zones, from 0 cents up to almost 70 cents. Each capture zone here is about 5 cents wide. Inside each capture zone, you can see 1 sagittal symbol, corresponding to the primary comma for that capture zone. Don't worry about the fact that you don't recognize some of the symbols yet. They aren't in the Spartan subset. We'll look at them later. The specific symbols don't matter now. And now we're ready to demonstrate how exactly the 13th harmonic is approximated. I pulled back up the diagram of the first 4 primes of the prime factor notation, upper left, so you can see how there, the 13th harmonic is represented by the left arc, right barb. I've also pulled back up the Spartan symbols and their 2-3 free classes, so you can see how the left arc, right barb actually also represents the prime factors of 5 and 7, together is 35. For now, don't worry about the fact that one is pointing up and one is pointing down. Just focus on the prime content. So the reason this works is that actually the 13 comma is quite close to the 35 comma. I'll pull up the cents for the 35 comma again. It's about 64.9 cents. And the 13 comma, it's at 65.4 cents. So it's only a half cent off, which no human can hear. Therefore, the sagittal symbol whose primary comma is the 35 comma makes a fine approximation of the 13 comma. So the sagittal GI notation essentially has you use the same symbol for both commas, and leans on the context of the chord or melody, or also the intuition of the player, to interpret it appropriately. Now, some of you may have a special piece of music which uses both the 35 comma and the 13 comma, and draws important musical distinctions between them. That's fine too. In that case, sagittal provides accents to let you distinguish them. We won't have time to take a closer look at accents today, though. But the 13 comma is just the first major comma, which is closely approximated by one of these symbols. Any comma you need will fall in one of these zones, and you should just use the symbol for that zone. If you're writing GI music using the more popular pitches, most of the time, it will be the primary comma anyway. But now you might protest, this diagram only goes up to about 70 cents. There are 1,200 cents in an octave. What about the other 1,130 cents? The answer is, this chart gives you all the information you need to know to find your notation relative to any given position on the chain of Pythagorean fifths. Think of it this way. Each pure Pythagorean fifth, or the frequency ratio 2:3, is about 702 cents. Think back to our spiral of fifths. After moving by 7 of these, or in other words, after cycling around all 7 letters of the Pythagorean nominals F, C, G, D, A, E, B, you've moved 4,914 cents. Octave reducing that is modulo 1,200, you get 114 cents. That 114 cent interval is what is indicated by the sharp or flat symbol in just intonation, and it's called the apodomy. 114 cents is still bigger than 70 cents though, right? Well, sure, but fortunately, the capture zone diagram we've been looking at is attached to every position on the Pythagorean chain in both an upwards direction and a downwards direction. And when you put both of them together, you can see that they have plenty of overlap. So don't worry, every position in the octave is covered. This doesn't even count the double sharps and double flats, which might be living around here too. Every position in the octave can be notated at least 2 ways, and sometimes 3, if it's also reached by the next to nominal ways, double sharp or double flat. Well, I've now probably convinced you that every pitch in the octave can be notated as sagittal, but I don't suppose you're excited, every time you need to choose a symbol, to prepare a huge diagram with many layers of flipped capture zones, etc., 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 and I don't blame you. But now that you understand the principles at work here, you're ready to use a tool that can do that for you. That's right. You don't really have to do any of those calculations, because there's an app for it. Well, not quite an app, but it's a spreadsheet you can download from sagittal.org, which does the trick. It's called the JI Notation Calculator, and it is pictured here. You simply enter your pitch as a prime exponent vector or ratio, and find at least a couple options for notating it, sometimes 3, depending, as just mentioned, on how the underlying chain of Pythagorean fifths lines up with respect to your pitch. By the way, this is one thing I'm working on now for sagittal, an actual web app that works for any possible sagittal notation, flavor, etc. We'll have it one day, but for now, this works fine, just for the JI notation. Now, you may be wondering, why does it say medium there in the top right? Well, that's just because the JI notation supports different precision levels. Here's what it looks like if you look further to the right in the JI notation calculator. The first section, the pink one, corresponds to the capture zones we've looked at already. In other words, that's the simplest JI notation precision level. insofar as it is the least precise, but requires the fewest symbols. Currently, 4 precision levels have been fully developed, and the 5th is still in progress. What this means is, if you're a stickler for accuracy, and you want to reduce the size of capture zones so that your approximated pitches are as close as possible, and you don't mind bringing in a bunch of new symbols in order to accomplish that, you can. But the reality is that almost no one should ever need to use these higher precision levels. They're just there if you really need them. For example, if you're doing some theoretical work. Because even the lowest precision level is not low precision. That's why it's not called low. It's already medium. At that precision level, your approximations will still always be within a couple cents. And that's fairly serviceable, for most humans anyway. So what we see here are the 4 precision levels of the sagittal GI notation which have been developed so far. Each next layer up, higher in precision, divides the range from 0 to about 70 cents into smaller chunks, using more symbols than the previous layer. The first layer uses only 12 symbols. The top layer uses 139 symbols, or, in other words, every symbol in the entire sagittal symbol system today. Again, you really probably don't need that much precision. Alright, now that you understand the concept of capture zones, we're ready to introduce a new sagittal notation which uses them in a different way, the 12 relative notation. This notation is called 12 relative because it is relative to a chain of 12 EDO fifths, rather than pure Pythagorean 2 to 3 fifths like the GI notation is. In 12 EDO, the fifth is exactly 700 cents. So in this world, moving around the Pythagorean nominals by 7 steps takes you exactly to 4,900 cents, which, modulo 1200, is 100 cents. So, in 12 EDO, the apotome, or sharp or flat, is exactly 100 cents. This is a fact that is probably quite familiar to most. What the 12 relative notation does, then, is provide its own set of capture zones, also extended up to a little past a half apotome, in order to ensure the entire octave is covered. But in this case, because the apotome is smaller, 100 cents instead of 114 cents, the half apotome is also smaller. So here we don't even go past 60 cents. We can leave off at around 57 cents. At first glance, these symbols look reasonably familiar. We've got the left barb, the right arc, the double barb flanked by the 2 combinations of arc and barb. But if you look closer, there's actually a bunch of sagittals you haven't seen before. There's even a flag, which 3 of these sagittals use, which you haven't seen before. This flag is called a boat hook. Let's get a closer look at it. So here's what the boat hook looks like compared with the other flag shapes. It's the curved flag which bends in the middle so that it's both concave and convex. And now we've met every flag shape there is in sagittal. 4 in total, designed to be as easy to distinguish from each other as possible. So let's get back to the 12 relative notation. Why or when would you want to use it? Well, the 12 relative notation is an excellent choice in a couple different situations. First, let's consider when your microtonal piece is neither written in GI nor in an EDO. For example, I've composed some pieces where the pitches are proportioned by the golden ratio, where the pitch system has nothing to do with the chain of Pythagorean fifths and is not approximated well by reasonably low EDO. Let's also say that my performers are not dedicated microtonal enthusiasts and are much more accustomed to reading staff notation as 12 EDO. In this case, it doesn't make sense for me to ask them to do the work of altering their interpretation of the conventional staff notation from 12 EDO to be based on some other fifth size than 700 cents. It's just going to make it harder for them to read, and it won't help their understanding of the music. In that case, the 12 relative notation is a perfect choice. Another situation where the 12 relative notation might help is if your piece is written in JI or some EDO, but your performers are really uncomfortable with microtones and not particularly interested in learning microtonal concepts like adapting to new fifth sizes. In these situations, the 12 relative notation can be used as a sort of slight finesse from simply writing the sense deviations on the page in numbers. You may only find that you need 2 or 3 of the symbols to fully notate your music, in which case it could still be a much better sight-reading aid than lots of teeny numbers on the page. An interesting aspect about the 12 relative notation is that every EDO notation for an EDO which is a multiple of 12 can be reconciled with these capture groups. In other words, if you pluck every 12n EDO from the periodic table of EDOs and line it up with the 12 relative notations capture groups, you'll see that each of its steps is notated with the symbol that it would receive if it were notated in the 12 relative notation. To be completely accurate, this only works up to a point. It only works so long as the 12n EDO shares its fifth size with 12 EDO. That is, the fifth of exactly 700 cents. But I don't think it's until around 300 EDO when the first 12n EDO occurs for which 700 cents is not the best approximation of the just 701.995 something pure fifth. And this just speaks to how darn good 12 EDO's fifth approximation is. So that brings me to the end of my presentation. We've really covered a ton of topics today. Let's recap. We learned a lot about sagittals themselves, like the 4 types of flags, barb, arc, scroll, and boat hook, element arithmetic, the mirror image principle, the size proportionality principle, and about multi-shaft symbols, like the X-shaft symbols, and the Revo flavor of sagittal which uses them. We also learned about 4 different notations: EDOs, found on the periodic table of EDOs, the prime factor notation, similar to many other microtonal notations, the JI notations, with sagittal's unique innovation of capture groups, and the spreadsheet calculator you can use to find them, and finally, the 12 relative notation, hybridizing the JI notation's capture groups with the one EDO which everyone knows and loves, or loves to hate, 12 EDO. There's many more topics to cover, from things we mentioned already, like accents, Sagispeak, EDO notation determination, and other symbol subsets besides Spartan, to things we didn't even mention, such as 2 entire other sagittal notations, long ASCII, which is the way of typing sagittals, comma naming, and more. I hope you're excited to learn more about all this. Normally I'd take questions at this time, but instead, I will see you at the roundtable discussion in a few hours. Thanks for your attention, and I hope you all are enjoying the event.